Every single day, your body takes your entire blood supply and basically throws 99% of the water and nutrients completely out of your bloodstream.
Right, just tosses it out.
Yeah, and then it desperately sucks it all back in just moments before it's lost forever. I mean, it sounds like a total evolutionary glitch,
It really does.
like an incredibly inefficient, maybe even dangerous way to keep a human being alive. But it is actually one of the most sophisticated chemical balancing acts in the known universe.
Oh, absolutely. We tend to celebrate the obvious showstoppers of human anatomy.
Right, like the heart or the lungs.
Exactly. You can feel your heart beating, you can watch your chest expanding. But the true masterclass in biological engineering is happening quietly in the back of your abdomen.
Yeah, you probably only think about your kidneys when you're stuck in traffic and desperately need a bathroom break.
Which is a shame.
It is. We culturally reduce this profoundly complex system to its most basic, visible output, basically a plumbing inconvenience. Well, for this deep dive, we are pulling from comprehensive medical physiology on the urinary system to completely shatter that assumption.
We really need to give the kidney some credit here.
Seriously. We're going to look at the actual mechanics of how these two fist-sized organs act as the ultimate master chemists. They are micromanaging your blood, your bones, and your survival, minute by minute. Okay, let's unpack this, because if you think the urinary system is just a biological trash compactor, you are missing the real story of human homeostasis.
The trash compactor myth is so pervasive. I mean, yes, it's true that the kidneys eliminate metabolic waste.
Like urea and stuff.
Yeah, urea from breaking down amino acids, creatinine from muscle metabolism, uric acid, and various toxins. That function is absolutely vital.
Right, because if that stops...
You're in trouble. If filtration stops, those toxins accumulate and become fatal rapidly. But eliminating waste is almost a secondary consequence of their primary job.
Which is what exactly?
It's strictly regulatory. They are meticulously balancing the exact volume and electrolyte composition of your body fluids.
And what's staggering is the physiological elasticity they have to maintain that balance. Looking at the data from the sources on how they adapt to extreme dietary swings, it really puts it in perspective.
Oh, the sodium numbers are wild.
Yeah, take sodium. A human can survive on a diet providing as little as 10 milliequivalents of sodium a day.
Which is barely a pinch of salt.
Barely a pinch. But, on the flip side, someone could consume up to 1,500 milliequivalents a day, which is the equivalent of eating several family-sized bags of heavily salted potato chips.
That is a 150-fold difference in intake.
And the kidneys just handle it.
They just handle it. Within 2 to 3 days of a massive sodium spike, the kidneys adapt and increase their sodium excretion to match that extreme intake precisely.
Wow. 2 days.
Yeah. During that brief adaptation window, you might retain a little fluid, which triggers a cascade of hormonal shifts, but then the balance is perfectly restored, and they perform this dynamic scaling for water, chloride, potassium, calcium, basically the entire periodic table of your body.
It makes sense that an organ filtering the blood would also balance the electrolytes in that blood. But when you look at the secondary functions, things get genuinely surprising. The kidneys don't just filter, they actively synthesize and secrete.
They're highly active endocrine organs, yeah.
Right. For instance, they secrete erythropoietin, or EPO, which is the hormone that dictates red blood cell production. I was trying to figure out why the kidneys, of all organs, are in charge of red blood cells.
It seems random at first.
It does. But if you think about it mechanically, an organ that receives a massive continuous flow of your entire blood supply is the absolute perfect monitoring station for systemic oxygen levels.
That is precisely the mechanism. The kidneys have specialized peritubular fibroblasts that constantly monitor the interstitial oxygen tension.
So they're like little oxygen sensors.
Exactly. When oxygen levels in the blood drop a state of hypoxia, these cells essentially stop degrading a specific protein called hypoxia-inducible factor.
Okay, and what does that protein do?
Well, that protein builds up and immediately triggers the transcription of the EPO gene. So the kidney floods the system with EPO, signaling the bone marrow to manufacture more red blood cells to carry more oxygen.
That is a brilliant closed-loop feedback system.
Yeah.
And they are doing similar regulatory work for your skeletal system too, right?
Yes, by converting vitamin D into its active form.
Right, calcitriol, which you need to absorb calcium from your gut. But the one that really caught me off guard was their role in glucose metabolism. Wait, my kidneys make sugar. I thought they just filtered things out.
It's surprising, isn't it? During a prolonged fast, the kidneys actually engage in gluconeogenesis. They manufacture glucose from amino acids.
I always thought the liver was in charge of that.
We typically think of the liver as the body's sole glucose factory. But during an extended fast, when the body is starved for fuel, the renal cortex ramps up its metabolic machinery.
So it's pitching in to help.
More than pitching in. It takes precursors like glutamine and synthesizes new glucose molecules, pumping them directly into the blood. In deep fasting states, the kidneys actually rival the liver in glucose production just to keep your brain functioning.
If we connect this to the bigger picture, it completely recontextualizes chronic kidney disease. It's not just a matter of toxins backing up in the blood. When that tissue is damaged, the entire systemic management grid collapses.
The whole system goes down.
Yeah. Patients with severe kidney failure often develop profound anemia because that critical cellular oxygen sensor is broken. The EPO signal just vanishes. Their bones become fragile because calcitriol drops, and their metabolic flexibility is severely compromised.
Which is why replacing kidney function isn't just about running blood through a dialysis machine to clear urea.
Right, it's not just a filter.
Exactly. A machine can mimic the trash compactor function, but it cannot easily replicate the minute-by-minute endocrine and metabolic oversight.
To pull off that level of continuous chemical management, these organs require unprecedented access to the circulatory system. This naturally brings us to the physical architecture. How do two organs, weighing only about 150 grams each, physically process the entire human fluid volume?
Well, it starts with the hemodynamics. The kidneys receive roughly 22% of your total cardiac output.
22%.
Yeah, that is 1,100 milliliters of blood rushing through these two small bean-shaped structures every single minute. For their size, they are the most highly perfused organs in the body.
That is a staggering flow rate.
Yeah.
And all that blood is being directed into the functional units of the kidney, the nephrons. The sources say you have roughly 800,000 to 1 million of these microscopic processing plants in each kidney.
Which is a good thing because you lose a lot of them.
Yeah, this part actually alarmed me. What do you mean you can't grow new ones? After age 40, you apparently lose about 10% of your functioning nephrons every single decade. That sounds terrifying for the listener.
It sounds like a catastrophic decline, I know, but the system is built with immense redundancy. The remaining nephrons undergo adaptive hypertrophy.
Meaning they get bigger.
Yes, they physically enlarge and step up their individual filtration rates. So an 80-year-old with 40% fewer nephrons can still maintain perfectly normal fluid and electrolyte balance.
Okay, that resilience is incredible. But looking at the microscopic anatomy of an individual nephron, the physical mechanism of how they actually filter the blood is fascinating. They use a dual capillary system connected in series.
What's fascinating here is the precise manipulation of fluid pressure. The blood first enters a tuft of capillaries called the glomerulus. This is a high-pressure zone operating at about 60 millimeters of mercury.
And for context, typical capillary pressure elsewhere in your body is vastly lower.
Vastly lower. So this intense, localized hydrostatic pressure forces fluid, electrolytes, and small molecules right out of the bloodstream. It pushes them through a fenestrated cellular sieve and into the starting tube of the nephron, which is called Bowman's capsule.
It's an elegant physical solution. You use pure mechanical pressure to force the plasma through a sieve, stripping away the fluid and leaving the large red blood cells and heavy proteins behind. But obviously, you can't just expel all that extracted fluid. You need to pull the valuable components back.
Precisely. Once the blood leaves the high-pressure glomerulus, it flows directly into a second network called the peritubular capillaries, which wrap entirely around the nephron's tubules.
And the pressure changes here, right?
Dramatically. In this second network, the pressure drops down to about 13 millimeters of mercury. So you transition immediately from a high-pressure expulsion zone to a low-pressure biological vacuum.
Wow, a biological vacuum.
Yeah, which perfectly sets the stage for rapid, massive reabsorption of the water and nutrients your body actually needs to survive.
High pressure to force the raw materials out,
Mm-hmm.
low pressure to selectively suck the refined materials back in.
Yeah.
So we have the high pressure push and the low pressure pull. Let's look at the actual volume being pushed and pulled, because the mathematics of this operation are almost unbelievable.
The numbers are staggering.
To understand how urine is actually formed, there's a fundamental physiological equation. Excretion equals filtration minus reabsorption plus secretion.
That equation governs everything. You filter a massive amount out, You selectively reabsorb what you need back into the blood, and you actively secrete any specific stubborn waste products from the blood directly into the tubule. The final product is what you excrete.
And the filtration rate is the number that stops you in your tracks. The kidneys filter roughly 180 liters of fluid every single day.
180 liters.
The average human only possesses about 3 liters of total blood plasma. That means your kidneys are throwing your entire blood plasma out into the nephron tubules 60 times a day.
And out of those 180 liters of raw filtrate, the body only produces about 1 to 1.5 liters of actual urine. Those low-pressure peritubular capillaries are pulling back over 99% of the fluid.
Here's where it gets really interesting. Because conceptually, filtering 180 liters just to reabsorb 99% of it sounds utterly absurd.
It does seem like a waste of energy.
It's like deciding to clean your bedroom closet by taking every single piece of clothing, throwing it all out onto your front lawn, and then carrying 99% of it back inside, folding it and putting it away, just to get rid of 3 old shirts.
That is a great analogy.
It takes an immense amount of metabolic energy. Why wouldn't the kidney just identify the waste in the blood and actively secrete only the waste?
It seems highly inefficient until you view it through the lens of evolutionary survival. Throwing everything on the lawn means that if an entirely novel, unexpected toxin enters your system, say, from a poisonous plant our ancestors ate, it is immediately flushed out of the bloodstream.
Oh, I see.
The body doesn't need to have evolved a specific specialized mechanism to recognize and secrete that specific new toxin. As long as the toxin is poorly reabsorbed by the tubules, the sheer volume of the massive filtration rate clears it rapidly.
So it's a brute force failsafe against the unknown.
Exactly. And secondly, processing the entire plasma volume 60 times a day provides the endocrine system with exquisite minute-by-minute control over the blood's composition.
So if things need to change fast, they can.
Right. If you need to drop your blood volume rapidly to lower your blood pressure, the mechanism is already running at 180 liters a day. The body just slightly tweaks the reabsorption rate and the problem is solved.
But that same precision also highlights how incredibly fragile the balance is. If your filtration rate increased by just 10%, going from 180 liters to 198 liters a day, and your reabsorption rate didn't perfectly adjust to match it, your urine output wouldn't just go up by 10%.
Not at all.
It would skyrocket from 1.5 liters to 19.5 liters a day. You would be completely, fatally dehydrated in a matter of hours.
That is why the cellular crosstalk between the filtration apparatus and the reabsorption tubules has to be flawless. And the tubules handle different substances in highly specific paradigms.
Right. The text shows how the system categorizes everything. Paradigm A is the purely trash pathway. A metabolic waste product like creatinine gets filtered out by the high pressure, and the tubules simply refuse to reabsorb it. It's a one-way trip out of the body.
And then you have paradigm B for electrolytes like sodium and chloride. They are freely filtered, but the body selectively reabsorbs a highly variable portion of them.
Depending on what you ate.
Exactly, actively adjusting the rate based on whether you ate that pinch of salt or the family-sized bag of chips. Then paradigm C is reserved for critical, high-value nutritional substances, primarily glucose and amino acids.
Which we definitely don't want to lose.
Right. These are filtered out into the tubule initially, but the cells lining the proximal tubule spend massive amounts of ATP to aggressively reabsorb absolutely all of it. Under normal physiological conditions, your urine should contain 0 glucose.
And finally, paradigm D, which covers organic acids, bases, and many foreign drugs. These substances are filtered, but to clear them even faster, the capillaries actively secrete extra amounts directly into the tubule. It's a highly customized, chemically intelligent sorting facility.
It really is, but once that sorting is fully complete and that final 1.5 liters of fluid has made it through the collecting ducts, its chemical composition is locked. It is officially urine.
Which presents a massive mechanical problem. We've perfectly balanced the blood, but now we've got 1.5 liters of highly toxic concentrated fluid sitting in the center of the body. If the fluid backs up and pressure builds, it will destroy the very delicate, low-pressure capillaries that just did all the work. How does it safely escape?
The journey outward is a masterclass in smooth muscle dynamics. The urine flows into the renal pelvis and down into the ureter's tubes about 10 to 14 inches long. But this isn't a passive gravity drain.
It's not just falling down the tubes.
No, the walls of the ureters contain smooth muscle that undergoes peristalsis. They actively drive waves of contraction to push the urine toward the bladder.
And there is a brilliant piece of anatomical safety engineering where the ureters meet the bladder. They don't just plug straight into the top. They enter at an oblique angle running diagonally through the bladder's muscular wall for a few centimeters.
Which is so important.
Yeah, that angle acts as a mechanical one-way valve. As the bladder fills and pressure rises, it naturally compresses that diagonal entry tunnel, preventing the toxic fluid from flowing backward up into the kidneys.
Because that backward flow vesicoureteral reflux can cause devastating kidney infections and scarring. The body protects the kidneys at all costs. You see this vividly with the ureterorenal reflex.
Oh, with kidney stones, right?
Yes. The ureters are heavily innervated with pain fibers. If a kidney stone drops down and obstructs a ureter, it causes agonizing pain. But those nerve impulses travel back up to the kidney and trigger an immediate reflex that vigorously constricts the renal arterioles.
So he just shuts the whole kidney down.
Basically, the body essentially cuts off the blood flow and turns off the filtration faucet in that specific kidney, preventing a pressure blowout behind the blockage.
A total localized shutdown to protect the nephrons. So assuming no blockages, the urine makes it safely to the bladder. The bladder is basically a muscular storage vault, heavily reliant on the detrusor muscle. And this muscle has a fascinating cellular structure. The muscle fibers are functionally fused together into a syncytium.
Meaning electrical signals pass seamlessly from one cell to the next.
Exactly. So when the signal to contract arrives, the entire bladder squeezes uniformly as a single unit.
But the real marvel is the neurological coordination of that contraction, the micturition reflex. It is a completely autonomic spinal reflex. As the bladder slowly fills, stretch receptors embedded in the bladder wall become increasingly active.
They're sensing the volume going up.
Right. They fire action potentials via the pelvic nerves directly to the sacral region of the spinal cord. The spinal cord instantly fires parasympathetic motor signals right back to the detrusor muscle, commanding it to contract.
It operates as a self-regenerating feedback loop. A tiny stretch triggers a contraction, which mechanically stretches the receptors even more, causing a faster volley of sensory signals, which triggers an even harder contraction. The loop builds to a sudden peak.
And if the environment isn't right for emptying, the reflex fatigues, the muscle relaxes, and the system resets, waiting minutes or hours before attempting the loop again. But as the total volume increases, these reflex waves become incredibly powerful and frequent.
So what does this all mean? It means that the simple act of holding your pee is literally an intense neurological tug of war. You have this ancient automatic spinal cord reflex desperately trying to empty the organ. But your conscious brain, specifically higher centers in the pons in the cerebral cortex, is acting as a strict supervisor.
It's constantly saying, not yet.
Yeah. The brain sends continuous inhibitory signals down the spinal cord to suppress the reflex and keep the external sphincter tightly locked.
And that external sphincter is controlled by the somatic nervous system. It is voluntary skeletal muscle. Your brain keeps it clamped shut until you consciously decide the time and place are appropriate.
And then what happens?
When you make that decision, your higher brain centers withdraw the inhibition, allowing the parasympathetic reflex to run wild while simultaneously commanding the external sphincter to relax.
It is a beautifully choreographed, high-stakes dance between your conscious, voluntary nervous system and your unconscious, autonomic nervous system.
This raises an important question, though. What happens when that intricate neurological communication line is damaged? Because the mechanics of micturition are so dependent on both the sensory stretch signals going up and the inhibitory signals coming down, breaking the circuit has profound consequences.
Right. If you cut the sensory nerve, say, from a severe crush injury to the sacral spine, or historically from diseases like syphilis, which destroy the dorsal root nerve fibers, the stretch signals never reach the spinal cord.
In that condition, which is called an atonic bladder, the micturition reflex simply cannot exist. The bladder fills with urine, stretching to absolute anatomical capacity, but the spinal cord has no idea it's happening.
That sounds dangerous.
It is. Eventually, the hydrostatic pressure overcomes the sphincter, and urine literally overflows a few drops at a time. The mechanical storage works, but the sensory trigger is entirely gone.
On the other side of the spectrum, you have the automatic bladder. This occurs if the spinal cord is severed higher up, above the sacral region. In this scenario, the local sacral reflex loop is completely intact.
The lower part still works.
Exactly. The stretch receptors sense the fluid, They tell the lower spinal cord sends the contraction signal, and the bladder successfully empties itself.
But the critical communication line to the brain has been entirely severed. The conscious mind has been cut out of the loop. There is no ability for the brain to send those inhibitory signals down to delay the
It
reflex.
just happens on its own.
The bladder simply operates on its own local timetable, initiating powerful, unannounced emptying purely based on volume. It perfectly illustrates how deeply reliant our modern social functioning is on a few invisible inhibitory nerve tracks running down the spine.
It fundamentally changes how you view the body. We've covered so much, from these microscopic filtration tufts processing 180 liters of fluid under immense hydrostatic pressure, to the renal cortex quietly manufacturing glucose and monitoring systemic oxygen, all the way to the complex spinal reflexes required to just sit through a long meeting.
It is a triumph of biological engineering. But if we step back and look at the whole picture, I think there's a profound evolutionary context here. Our kidneys evolved over millions of years to perform these absolute miracles of homeostasis in environments of scarcity.
When resources were hard to find.
Exactly. They were designed to fiercely guard every drop of water and selectively reclaim every single molecule of sodium to save our ancestors from dehydration and famine. But think about the environment we live in today.
An environment of absolute, inescapable abundance.
Exactly. How might our modern daily diets of ultra-processed foods, massive sodium loads, and constant sugar intake be quietly tricking the very survival mechanisms that kept early humans alive? We are subjecting these delicate, low-pressure reabsorption networks to a continuous physiological stress test they were never historically meant to endure.
Wow.
The master chemists are working overtime just to keep us stable in an environment of unprecedented excess.
That is a fascinating and genuinely sobering perspective. It makes you realize that every single glass of water you drink and every salty meal you eat is a new variable entered into a massively complex biochemical equation running in the background of your life.
It never stops.
It really doesn't. So, the next time you're stuck in traffic, don't just think of it as an inconvenience. Think about the silent high-pressure filtration plants and the intense neurological tug-of-wars keeping you alive and perfectly balanced. Thank you so much for joining us on this deep dive. Keep learning, keep questioning, and stay curious.